Chapter 9, Chemical Quantities. Those are the things we're going to be looking at. So we're going to revisit chemical equations and what they mean. A balanced chemical equation is going to give us relative numbers of reactant and product molecules that participate in a reaction. Remember that mole is a counting unit, and so if we are looking at numbers of particles, we could also look at dozens of particles or at moles of particles. And the coefficients in that balanced equation are what give us the relative number of molecules. So we learned how to balance equations, and we did that by putting coefficients in front of the formulas. So chemical equations are a lot like recipes. Chemical equations are a lot like recipes. So here's an example of a recipe for a sandwich. 2 slices of bread, 3 slices of meat, 1 slice of cheese. Done, got a sandwich. So if we're making sandwiches, then we need to know the ingredients. Those are the reactants in a chemical equation. And we need to know the amounts of ingredients. Because I've been in a situation where I had to make sandwiches for the football team. Okay, so you're making lots of sandwiches. So fine, you need to know, well, what do we need for sandwiches? We need bread, meat, and cheese. Okay? It's not enough to know that you just need bread, meat, and cheese. You need to know how much. Because if you've got 1 piece of bread, you have bread, but you don't have enough to make 35 sandwiches, right? So you need to know the amounts. A recipe can be scaled up to make larger amounts. Now, most recipes are made to serve 4 people. I have 6 kids, and some of them eat a lot. And so we usually triple recipes, So theoretically it should serve 12, and if we're lucky it serves 8. But you can scale it up. How do you scale it up? You just multiply everything. If you double a recipe, then you double all the amounts, right? So if we're going to make 100 sandwiches, we're just going to multiply all those coefficients by 100. So instead of 2 slices of bread, we need 200 slices of bread. Instead of 3 slices of meat, we need 300. And instead of 1 piece of cheese, we need 100. And then instead of 1 sandwich, we'll get 100 sandwiches. Does that make sense? You just multiply them all by the same number. And you have the same ratios. So 200 to 300 to 100 to 100 is the same ratio as 2 to 3 to 1 to 1. That's the same as the ratios of the coefficients in that balanced equation or the recipe. Everybody with me on that? Let's look at this one. So this isn't a recipe for making sandwiches, but it's a chemical recipe. It's a chemical equation. So C2H5OH, which is ethanol, plus oxygen, that's a combustion reaction. It'll burn and form carbon dioxide and water. This equation is balanced. We learned how to do that. So there's 2 carbons here, and there's 2 carbons over there. And here we've got 5 plus 1 is 6 hydrogens, and over there we've got 6 hydrogens. We can go through the whole thing, it's balanced. When an equation is balanced, then all the atoms that are present in the reactants are accounted for in the products, because we can't have atoms appearing and disappearing. All we're doing is rearranging them. When you are making sandwiches, all the bread that you started with ends up in the sandwiches. You don't have bread disappearing. Now, in the kitchen, yeah, you do have bread disappearing, because somebody comes and they're hungry and they snitch a piece of meat, right? That doesn't happen in chemical equations. So all the atoms are accounted for. We can interpret these equations in different ways. We can say 1 molecule of ethanol reacts with 3 molecules of oxygen to form 2 molecules of carbon dioxide and 3 molecules of water. That's in terms of particles. Or we could say in terms of moles. We took the sandwich recipe and we multiplied by 100. When we make this into moles, we're multiplying by Avogadro's number. So we're putting the word mole in here. Mole means 6.022 times 10 to the 23rd things, right? And that first one, there's no number, but it would be 1, right? 1 mole. The mole interpretation is the one that we use the most, because we never do reactions where we've got one molecule reacting with 3 other molecules. That's way too small. Molecules are too small to do that with. We do with larger amounts. Okay? Any questions yet? So here's a concept check. One of the steps in producing copper from copper ore is this reaction. Copper 1 sulfide plus copper 1 oxide gives copper metal and sulfur dioxide. And it says in parentheses, this is unbalanced. After balancing the reaction, determine how many dozen copper atoms could be produced from a dozen molecules of the sulfide and 2 dozen of the oxide of copper. And then it also asks how many moles. Well, let's deal with the first thing first. First thing is we have to balance this equation. So let's look at that. On the left side of the equation, how many copper atoms are there? There's 2 in the first one and 2 in the second, so 4. So we're going to need a 4 here. And then on the left, how many sulfurs? Just 1. And on the right, how many sulfurs? Only 1. So that one's okay. Let's look at the oxygens. On the left, how many oxygens? 1. And on the right, 2. Darn it. Okay, so then we have to put a 2 here. So we've got 2 oxygens on the left, 2 oxygens on the right, but that messed up the copper, didn't it? So now on the left, we have 2 coppers here and 4 here. And so we're going to need to change this into a 6. And now it'll be balanced. So we had to balance it first. And then it says after balancing, how many dozen copper atoms could be made from a dozen molecules of the sulfide and 2 dozen of the oxide? Well, this is the sulfide and this is the oxide. So they're asking us how many copper atoms, that's our question, how many of these, and they're saying we've got a dozen of the sulfide, so 1 dozen of those, and 2 dozen of these. So it's asking us in terms of dozens, which is nice because we know what a dozen is. A dozen is 12. What's the equation telling us? 1 of these reacts with 2 of those to make 6 of these. If we said 1 dozen of these and 2 dozen of those, how many dozen of those would we get? 6 dozen.
So you use the coefficients.
We use the coefficients. Because they give us the relationships. So if a dozen of the sulfides and 2 dozen of the oxides react, it would give us 6 dozen copper atoms. What if it was moles? What if it was 2 moles? 1 mole of this and 2 moles of that. How many moles of copper would we get? 6 moles. I need to rearrange this slide. I'm not liking it very much. Do you see the coefficients are telling us how much of each we need? Dozen and mole are both counting units. And so those coefficients can be interpreted in more than one way. We can have individual number of atoms or molecules, or we can have dozens, we could have hundreds or millions, or we could have moles. So then the correct answer is going to be D, isn't it? we'll get 6 dozen copper atoms if we do 1 and 2 dozen of the reactants, and we'll get 6 moles of copper atoms if we do 1 and 2 moles of the reactants. Any questions?
Would you do the same type of question if you were asking for the sulfur dioxide?
Mm-hmm.
So you would have one.
Yeah, so what about the sulfur dioxide? So if we're doing this, the one with the dozens here on the bottom, 1 dozen copper sulfide, 2 dozen copper oxide, we figured out that's going to make 6 dozen copper atoms. How many dozen sulfur dioxide? Just 1. So we'll get 1 dozen of that. And if we do that in terms of moles, we would end up with 1 mole. So the coefficients are multi-purpose. They can mean number of particles. They could mean number of dozens of particles. They could mean hundreds or millions or trillions of molecules or moles of molecules. Very important concept. Any other questions? So let's look at this some more. Balanced chemical equation can predict the moles of products. So in this example, we have water decomposing to form hydrogen gas and oxygen gas. So when we look at this equation, we need to be able to interpret it and understand what it's meaning, not just some random series of numbers and letters. So 2H2O. One way to interpret that is that there are 2 water molecules. So here we have pictures of the water molecules. The 2 means there's 2 of them. That's not part of the formula for water. It's telling us how many. So there's 2 water molecules, and that's going to make 2 hydrogen atoms. Sorry, hydrogen molecules. Each hydrogen molecule has 2 hydrogen atoms stuck together. There's 1, there's 2. And it will make 1 oxygen molecule. And we can see that that's balanced also. Let's see, what do we do here? Because here this red one goes over here and the other red one goes over there. They're both accounted for. And these blue ones go over here and these blue ones go over there. So nothing appeared, nothing disappeared. It's like playing with Legos. You had these little things, you took them apart, you put them together in a different way. Nothing appeared, nothing disappeared. Conservation of mass. That's what the chemical equation means. Question?
It's kind of just more about the water. You said that's a decomposition of water?
This is a decomposition reaction, yeah.
So what would be the cause of that?
What would be the cause of that? Electricity could be the cause of that.
Running electricity
Yeah.
through the water?
You can actually do that at home. Drop a 9-volt battery in a cup of water.
And then the bubbles are...
The bubbles on one side are oxygen, on the other side are hydrogen. Yep.
And then what happens when they're actually, when those gas bubbles hit the water, they're just going to the top and...
They just float up and they escape into the air.
So if you had enough electricity running through the water would eventually be gone?
Yes. Yep. You can destroy water. That was kind of an evil laugh. Yeah, you can destroy water. You can also make water.
Because of heat?
What happens when you burn hydrogen gas? It makes water.
Oh, yeah.
The hydrogen reacts with the oxygen. That's a combustion reaction and the product is water. It's the opposite of the decomposition of water.
So I could get a tank of hydrogen...
And burn it, and you get water.
Collect water from it?
You could, yes.
So why don't we do that?
Well, hydrogen's, yeah, I mean, the idea of a hydrogen-powered vehicle is a great idea because it wouldn't cause any pollution, right? Hydrogen burns very, very cleanly. A problem with hydrogen is it's also very explosive. Yeah, you remember the Hindenburg?
Yeah.
Yeah, big blimp full of hydrogen. Bad idea. Yeah.
It's also surrounded by like canvas.
Well, yes, there were so many things wrong. That was like epic failure, right? Epic failure. But we learned something. Now we don't fill our blimps with hydrogen anymore. We fill them with helium because helium doesn't burn. But yes, in theory, you could do that. The problem is practicality and cost.
But I meant more of just as an experiment.
As an experiment, you could absolutely do that. You could, definitely. So that's one way to interpret this equation. But what if we doubled it, like doubling a recipe? Then we're doubling everything. So instead of 2 molecules, now we have 4 molecules. If we start out with 4 molecules here, we're going to end up with 4 of those and 2 of these, because everything gets doubled, just like in a recipe. So we can interpret this in this picture way with the number of molecules, or we can do it in terms of moles. So 2 moles and 2 moles, and this would be 1 mole. If we can double it with numbers of molecules, we can double it with numbers of moles. So 2 moles yields 2 moles of hydrogen and 1 mole of water. 4 moles of hydrogen would yield 4 moles of hydrogen gas and 2 moles of water.
So if you talk about molecules, then you're talking about individual molecules, but when you use the term mole, then you're talking about Avogadro's number.
Right.
Which would be a lot.
Huge number. Yes. When I'm talking about molecules, it's individual particles. 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 Made up a new word there. Mole is unfortunately similar to the word molecule, and it looks like an abbreviation for molecule. There's no abbreviation for molecule. Mole is not the same as molecule. It is like a dozen, but it's this ginormously huge number of things. And so that's something that is hard to get your brain around at first. And I think I have students who get all the way through chemistry class, and they never really understand the difference between a mole and a molecule. A mole is a dozen. But instead of 12, it's that other number. A mole is a dozen, okay? It's a number of things. So it's a very good question, very good point.
Times the negative 1, 10 to the negative 23.
We can't use masses, either grams or atomic mass units, directly with equations. We'll learn how to deal with that later. Anybody else have any questions about this? I'll assume that you guys are all chatting about chemistry. Yeah.
Back to my other question.
Okay.
In chemistry, do we figure out how much energy is produced from a reaction?
We can do that, yes. Yep. First, we're going to... My computer's upset because it's not connected to the internet. Yes, I know. You can't... We can calculate the amount of heat given off by a certain chemical reaction. First, we're going to learn how to predict, if we start with this mass of reactant, how many mass, what mass of product will we make. But you can also do it in terms of energy. Like if you're burning, for instance, butane, and you need a certain amount of heat energy out, a certain number of kilojoules, you can calculate how much butane in grams you would need to burn to generate that much heat.
That's cool.
Yeah, the eyes got big. That's interesting, huh? So we're going to look at mole ratios. Mole ratios help us to convert from moles of one substance to moles of another substance. You guys talking about chemistry?
Yeah.
Okay. I feel a little better. You know, this is all going up on YouTube. Yeah. So mole ratios. This helps us to convert from moles of one thing to another. The ones we've been doing so far have been nice, easy numbers. We've been like doubling it or multiplying by 100, and it's been nice little whole numbers and everything. But of course, life isn't like that. So let's look at this. Consider this equation. Can't even say it. Na2SiF6 plus 4Na yielding Si plus 6NaF. Right, that's a mouthful. Especially in this class, I'm not going to try to trick you by giving you an equation that looks like it might be balanced, but it isn't. So if you're given an equation that has coefficients, you can pretty much assume that that's a balanced chemical equation. What I do in Chem 10 is I try to separate things. And so if I want you to balance an equation, especially on an exam, I'm going to just have you balance it. And if I want you to use a balanced equation, we're going to use it separately. I'm not going to combine those all into one big hairy problem. That's for future chemistry classes. We'll do that to you, but not here. So this one, we don't need to check it. You can check it if you want, but that one's already balanced. The question is, how many moles of sodium fluoride will be produced if 3.50 moles of sodium is reacted? Okay, if it was saying 4 moles of sodium, then it would be easy, right? 4 moles of sodium would produce 6 moles of sodium fluoride. But it's not nice numbers. So then we have to learn how to use mole ratios. So we can write conversion factors from the chemical equation. Because for every 4 moles of sodium, you're going to get 6 moles of sodium fluoride. You can take any 2 reactants, products, one of each, and set them equal to each other. It's only true for this reaction, but we could also say that 4 moles of sodium would equal 1 mole of silicon. Because what the equation tells us is that if we react 4 moles of sodium, we will get 1 mole of silicon. And so those are equal, and those are conversion factors. They don't look like conversion factors yet. But what we're going to do is we're going to say we've got 3.50 moles of sodium, and it's asking us how much sodium fluoride. So we're going to multiply by moles of sodium fluoride, because that's the unit they're asking us to find. And we're going to divide by the unit that we were given, moles of sodium. This is dimensional analysis again. So the units tell us what to do. We put the units in there so the units work out. And then we go looking for numbers. Well, what's the relationship between moles of sodium fluoride and moles of sodium? Well, there's 6 moles of sodium fluoride made for every 4 moles of sodium that react. These ratios are like the easiest conversion factor ever. You just look at the equation that you're given. So here's sodium. In front of the sodium is a 4. So then in front of moles of sodium, you write 4. In front of NaF is the number 6. So in your equation, you've got moles NaF, you write the number 6. And then you get out your calculator, which I forgot to get out. And we've got 3.5 times 6 divided by 4. And the calculator is going to give us the answer, 5.25 moles of sodium fluoride. This is a very important concept. Any questions? Do you see what I was doing there?
We're doing the same equation, and usually, like, say the coefficients were bigger numbers, and they are still like in an even ratio. Like, can you reduce it? If you reduce this, will be like 3 to 2.
Can you reduce the numbers in the mole ratio if they're large and reducible? Yes, you can. I don't see the point. There's not really any point in doing it, but you could. And in fact, 6 to 4 is a ratio that could be reduced to 3 to 2. Would you get the same answer? Yes. I advise, though, just sticking the numbers in, and you're going to use the calculator anyway. Just do it on the calculator. But yes, you could. And there's, our balanced chemical equations are mostly going to be lower ratios anyway. We're not going to end up with crazy, huge numbers or anything. It's a good question, though.
Because get reduced?
Yeah,
to the
because
smallest
we
thing,
reduce the
right?
coefficients to the smallest ratios that we can. Now, we can't reduce the 4 and the 6 in this equation because we also have coefficients of 1. And so this is the lowest ratio considering all the
It
reactants
has
of
to be
products.
all of them, right?
You have to consider all of them with the whole equation. In this particular calculation, we're looking at the relationship between 2. And it happens to be 6 and 4, which are both divisible by 2. And so you could factor a 2 out if you want to. You know, and some people enjoy stuff like that. And
So why not just write a balanced equation when you write a chemical reaction?
well, usually we do. That's a balanced reaction.
So this whole time when they weren't there, it was just to get us there.
Yeah, when we've been writing the unbalanced equations, we did that because we're teaching you how to balance equations. Because sometimes you're just given the reactants and you're expected to predict the products and then balance it yourself. And so it's important to know how to balance an equation.
So whenever we would see, say there was no coefficients in there, and there was just Na2SiF plus 4Na,
Right.
or plus Na. In reality, it's one molecule of that and 4 or whatever.
Right. If I gave this equation to you without any coefficients, that doesn't necessarily mean that that's actually what's happening because it would have to be balanced. And so if you see an equation without any coefficients, you should investigate it and see if it's balanced. Some are balanced without coefficients because it's 1 to 1 and produces 1 and 1. But most are not. If you're given one with the numbers in there, it's pretty safe to assume for this class that it is balanced.
Because I don't know, what I'm getting at is so okay, say to make water, right? It really it's H2 plus O2 equals H2O.
Right.
But in reality, it's not, right? It's H2 plus O2 equals a different number of H2O molecules.
Right. These H2 plus O2 producing H2O tells us what compounds or elements are reacting and what's formed, but it's not giving us the relationship between particles. Because if you did this, you'd have an oxygen atom left over, and that can't happen. And so a balanced chemical equation reflects what actually happens. And so we would need a 2 here and a 2 here. And then, no, I did that wrong. We need a 2 here and a 2 here. Because it would take 2 molecules of hydrogen and 1 of oxygen. In reality, that's... The balanced chemical equation is what's actually happening. Yeah.
Because that's what I guess the underlying question was, if the coefficients were different, you wouldn't get a different product.
Correct. Yeah. Okay, any other questions?
What does it mean reacted with excess? Extra?
Excess. Okay, excess means there was extra. So, like if we think back to the sandwiches,
How do you have leftovers?
well, when you're making sandwiches, like say, last year my husband was making sandwiches for the kids for lunch, fancy sandwiches. He was like cooking chicken and then slicing it, and these were like nice. But he would use an entire loaf of bread, because some of my kids will eat 2 or 3 sandwiches. So an entire loaf of bread for one lunch. For everybody. Okay, and so you're going through and you're making these sandwiches, you're making, 8 sandwiches or whatever, and you use up all the bread. Did you necessarily use up all the meat and all the cheese? Could there be some left over? That's why you go back and get more bread, right? In a chemical reaction, and we'll learn this in a few minutes, it's going to react until you run out of something. You're making sandwiches, you run out of bread, you have to stop making sandwiches.
Without balance, how can there be leftovers?
It'll make more sense when you're limiting it.
Yeah, he's right. It will make more sense when we get to the next part. But what it means by excess is that there's plenty of the other thing. You don't need to worry about whether there's enough or not. So that's what excess means. So let's look at this one. Propane, common fuel in heating homes in rural areas. So you go outside Reedley very far and you'll see houses with propane tanks. Little background information there. Is it necessary? No, not at all. Predict how many moles of carbon dioxide are formed when 3.74 moles of propane are burned in excess oxygen according to the equation. And so here, imagine burning propane. You know, are you going to use up all the oxygen that's present in your house burning up the propane? Hopefully not, right? Because you want to be able to breathe. So there's extra oxygen. You're just going to use what you need. But every mole of propane is going to use 5 moles of oxygen. If there's other oxygen around, it'll just stay there. But it's not going to participate in the reaction. Okay? So this is asking if we have 3.74 moles of propane. So one way you can organize information is use the chemical equation. So when you're doing work, you should write the chemical equation on your paper and then use it to help you organize. So I still have that. I want a different color. Under propane, I'm going to write 3.74 moles. Because it told me I had 3.74 moles of propane. And then it's asking how many moles of CO2. So under CO2, I'm going to put a question mark, mole. Because that's what I'm trying to find. And so then that gets rid of all those words that are so confusing. And we can just look at this and say, oh, we got 3.74 moles of propane, and we want to know how many moles of carbon dioxide. And so then we can do our little equation, 3.74 moles of C3H8. And we want to convert this into moles of CO2. So we're going to multiply by moles of CO2, and we're going to divide by moles of propane. Because we want the units to work out. The units tell us what to do. We get the units in place, and then we go figure out what numbers we need. The numbers for mole ratios come from the equation. We look in front of propane. What number is there? It's a 1. It's implied. It's not written. And so you don't have to write it down here, but a lot of students want me to, so I'll write the 1 down there. 1 mole of propane will produce how many moles of CO2? 3. So I'm going to get 3 moles of CO2 for every 1 mole of propane. The units tell us what to multiply and divide by. And then we just use our calculator. So we have 3.74 times 3 divided by 1, or 11.22 moles of CO2. That's what the calculator told us. This is a multiple choice question. So which is the best answer? It's A. It says 11.2. It doesn't say 11.22. Is that a problem? No, it isn't, because we started with 3 significant figures. Right here, 3 sig figs. And so this should really be rounded to 3 significant figures. So we would just drop the 2 and get 11.2. Any questions?
So if you were to ask a different question about, let's say, how many moles of CO2 would be formed when 3.74 moles of oxygen would burn, then you would take into account the oxygen molecule, the
Right.
502.
Yep, so let's do that one. Let's say we had 3.74 moles of oxygen instead, and we're curious about how much CO2 would be made. So now we're going to start, I'll do this up here on top. We're going to start with 3.74 moles of oxygen. We're going to multiply by moles of CO2 because that's what we're looking for. And now we're going to divide by moles of oxygen because that's what we started with, and we want the units to cancel out. Then we go look at the equation, and we see in front of CO2 is the number 3, and in front of oxygen is the number 5. So now we'll take 3.74, we'll multiply by 3 and divide by 5, and we'll end up with, I'll round that off, 2.24 moles of CO2 if we burned 3.74 moles of oxygen. You can do this relating any two reactants or products. You could find out, well, if I had 3.74 moles of propane, how many moles of oxygen would I need to react with that? Or if I produced 11.2 moles of CO2, how many moles of water would be produced? So we can connect any two in the equation. And some equations have 4 or 5 or 6 products or reactants. Even on the same side. Even on the same side. So if I had 3.74, just because we're using that number, if I have 3.74 moles of propane, and I want to know how many moles of oxygen do I need, I want to make sure I have enough oxygen, then I would multiply by moles of O2 and divide by moles of propane. So the units work out. Then I go to the equation. In front of oxygen is a 5, and in front of propane is a 1. 3.74 times 5. 18.7. So that's telling us if we're going to burn 3.74 moles of propane, we need to have 18.7 moles of oxygen. So any two. You can do 2 products, 2 reactants, start with a product, find a reactant, start with the reactants, end with a product. It's one concept, and then you can do all these different things. That's what I like about it. It's not you memorize a different equation for everything you need to calculate. One process, and then it just applies to so many, many things. Any other questions? That's the end of that section.